How do I present on this? Oh. Okay, so Naya and I reviewed Eudesmol, which is a drug that is found a lot in like different perfumes and specifically in eucalyptus oils. So we kind of guessed might smell like eucalyptus or like minty. So this is its structure. We're just going to talk about the two synthesis pathways that have been used to produce it. So this is the first pathway. Sorry, it's a little bit blurry, but most of the steps are pretty simple, but we can walk through them just one at a time. So the first step is an acetal reaction. So you can see here, the acetal is combined with like the OH, carbon-carbon OH, and the tosylate is used to protonate it to do so. And then we assume that this bond shifts because of resonance from
Oh,
here.
I didn't notice that.
Yeah, that's what is it maybe something else or? Okay. Oh,
Yeah, no, I don't know.
sorry.
I mean,
No, that's okay.
yeah.
Okay, well, the bond shifted,
Yes.
so that's still up for question of why. And then the second step was an anti-Markovnikov hydroboronation, where the borohydro group and the THF were used to add an alcohol here, and this alcohol is eventually going to become a ketone through Jones's oxidation, which basically Jones's oxidation will turn primary alcohols into carboxylic acids and secondary alcohols like this one into ketones. So it's just a
Nice.
general oxidation step. And then
This is just totally classic so far, right?
yeah. So this step is a little new. It's called epimerization. So an epimer is one of the pairs of diastereomers. So it's turning this epimer into another one. So basically this wedge becomes a dash, and that's all that's happening there.
So do you see why that's possible?
What do you mean?
Like, so like based on what they're treating the compound with, like how are they getting that to work, I guess? You know what I'm saying?
Yeah, is it just like hydrogen is just adding from like behind, and then this hydrogen is leaving? Is that what you're asking?
Well, of reagent are they treating it with? Does it look like to you?
Oh, like an acid and a conjugate base.
No,
Like a
no. So
salt?
it is a salt. So it's sodium methoxide, which is similar to sodium hydroxide.
Mm-hmm.
Okay.
So if you took that compound and you treated it with sodium methoxide, or what kind of thing are those types of things, I guess? I mean, what would they do if you treat a compound with that?
They would like remove hydrogens.
Yeah, they would act as a base. Yep. And what is the most acidic hydrogen in the molecule?
This
The
one.
one that's closest.
It's the one that's alpha to the carbonyl. Yep.
Mm.
So you can remove that and make the enolate, and then you can put it back on, but then you have a choice about what side. It could go back on the bottom. It could go back on the top, which would just make the starting compound, or the bottom. Do you see what I mean?
Mm-hmm.
Yeah. So that way you can scramble that stereochemistry at that position. You can equilibrate it to whichever one is better. And the down arrow or the dash bond is probably better. Well, just the fact that it works means that it is better. And it's probably better because in a chair conformation, I think that I think the top compound is sort of like a little boat-like, and then the bottom one is probably better chairs, if you follow my meaning.
Mm-hmm. Okay,
Okay,
that
that's a
makes
little
sense.
weird. All right.
Okay, so this next step is just a Wittig reaction. So to this ketone, they're adding this CH2 group. So this is just one of a general reaction we've learned before in Orgo. This next reaction is just like reverse acetal reaction, so acetal hydrolysis, where they're like removing this OH, CH2, CH2, OH, and it's just becoming this ketone again. So why they did that, I'm assuming they did that to isolate this ketone that they were doing all the reactions to, which is why they like protected this through an acetal, is my guess. This next step is just reduction through the LiALH4, and then it's this ketone now is being protected by the tosylate group. So they're kind of just doing different Wittig and acetal reactions to isolate which ketone they're wanting to work with. And then this reaction it inverts the stereochem of the tosylate, and then it's going to add the CN. And I'm not sure in what particular order, if it happens at the same time, but that's just what this reaction does, is it replaces this oxygen tosylate with the nitrile group and with the opposite stereochem.
Do you know what reaction that is? What's the name of it?
No. Not like off the top of my head. I'm sure we've heard of it though.
I think you have. So tosylate is like a leaving group. It's not really a protecting group. It makes the alcohol into a leaving group.
Mm-hmm.
And you're treating it with cyanide, sodium cyanide. It goes with inversion.
Cyano inversion?
Huh?
Cyano inversion? I don't know.
It goes with stereo, or it goes with so-called Walden inversion. Naya, sorry,
No idea.
making her uncomfortable. So this is an SN2 reaction.
Oh, okay.
Oh,
That's not
okay.
what I thought you meant.
Okay, so like it all happens at once, you mean?
Yeah, so it's just a nucleophilic substitution with stereochemical inversion. Yeah.
Oh, okay. Well, that makes sense.
Yeah.
I see that.
That other compound, I guess, is like the solvent, which is a weird solvent. But
Throughout both of these reactions, they seem to pick like kind of weird solvents. I mean, I don't know. They seem weird. All right, and so this next step 9, they're replacing this nitrile group with like this ketone, which seems like kind of weird, but here's the mechanism for how they do that. So using this lithium methyl, I forgot to put the 3 here, has been common. Like it's in this reaction, and they do it again in Naya's reaction using the methyl lithium. So the carbon is negatively charged, it's dissociated from the lithium, and it's going to add to this carbon of the nitrile here. Nitrile is going to steal a hydrogen and steal another hydrogen so that it can be prepared to leave. So now this alcohol group here, its electrons are going to move down. Oh, I went the wrong way. So this
I see.
water here is being added, and then this nitrogen is going to steal hydrogen from the water. Electrons will move down, nitrogen moves out, and then the nitrogen steals that last hydrogen on this soon-to-be carbonyl.
Yeah.
So that's what happens there.
It's kind of a nice thing because I know coming up there's places where 2 methyl groups get added, right? So this is a way that you can sort of trick it to stop once and give a ketone, because that second molecule, see how like it's like a carbon nitrogen double bond with the anion?
Mm-hmm.
It'll just sit there until you quench the reaction. Like the ammonium chloride that starts all the second part, that would be like you would add the methyl lithium first, and then it adds one time, and then it sits there until you decide to like just quench the reaction by adding a bunch of aqueous ammonium chloride to it, and then it converts that thing into the ketone afterwards. You know what I mean?
Yeah.
So it's kind of a nice way to do it.
Yeah. Yeah. So they do that here, and
You
then the
make this
next.
in ChemDraw?
Yeah.
Dang.
Thanks. But they do that kind of what Scott was talking about also is done here. So they'll add the methyl lithium only once because they already have methyl here. So let's say this methyl is this red one, the new methyl is this black one, and this oxygen gets protonated by some acid that just isn't listed, but we know it's there. So it kind of simply just looks like this again. The methyl lithium is dissociated, adds here, electrons move up, and then protonation with the acid to get the alcohol. That's what happens there. And then I'm going to turn it over to Naya.
Okay. Oh, wait, hold on, let me like.
Is everybody 20?
I think so. Well, except for Emily.
Well, Emily's older, presumably, right?
Mhm.
Yeah.
Okay.
All right.
So this is the second synthesis of Eudesmol. This is a reaction that happened later, and it was done by Spencer. So I'm going to walk you through some of these steps. So in the first step of the synthesis, it's an acetal reaction where a diol is turned into an acetal using toluene sulfonic acid. And then they did, right here, they did an ozonolysis reaction where they turn an alkene into an aldehyde.
An aldehyde.
I'm sorry.
Yeah.
Yeah. Okay, and this is the mechanism for it.
Oh my God.
So this oxygen here goes after this, I guess, like, what is this, like the beta position of the, or is it the alpha position of this alkene? I don't know.
I would call this a 3+2 cycloaddition.
Okay. Okay.
See how it looks a little bit like a Diels-Alder reaction? A little
yeah,
bit.
okay. Yeah.
So a Diels-Alder reaction is a 4+2. The diene is 4 atoms, and then the dienophile is 2, and then this one is like 3+2. Yeah.
Okay.
Yeah.
So this oxygen goes here, then the bond from here goes to the oxygen, and this double bond brings the electrons down to this oxygen, and then in this step you kind of have, I guess, I don't know, like some sort of like cyclic, like formation, I guess, and then it turns into an aldehyde. I mean, an aldehyde. Then in this second step, so this is a reaction we actually haven't seen before. It's called the Appel reaction or the Appel reaction, and it converts an alcohol into an alkyl halide. In this case, it's a chloride, using triphenylphosphine and tetrachloromethane, and it's a very stable sort of reaction. In this third step, they use Gilman's reagents, and that's used to perform conjugate addition to the alpha beta unsaturated ketones, and they're good nucleophiles for SN2 reactions, and they're kind of similar to, we thought it was like a Grignard, some sort of Grignard at first, but then we kind of realized that Grignard reagents are not generally good for performing SN2 reactions. And then in this part of the synthesis, you have another acetal hydrolysis using calcium chloride, and that puts on a tosylate group on these 2 carbons. Then in this step, this is a little like tricky, I think, to like kind of understand like in your head, but it's a carbon-carbon bond forming reaction essentially, where this this carbon on this ketone forms an enolate, causing the toxicity group to leave, and then the bonds just kind of form from there.
That's nice.
Oh, wait, and
Oh,
also
excellent. Go
this
ahead.
is like Scott, you had said it's a one of the Baldwin rules. Like it's or like looks like one of the
It
Baldwin
is.
rules. This is 6-hexotet. Yeah, so in this mechanism, I guess we provided the H's or the hydrogens to kind of see better what we're looking at. So this oxygen goes to the hydrogen, that bond forms here. Then you have here where the enolate's formed. And then this
Ooh.
carbon, oh, it's not. It's supposed to be negative.
Yes.
Okay.
Yeah.
Yeah.
All
So
right,
that.
we'll pretend that's
Okay.
a negative sign or a minus sign. And yeah, so this negatively charged carbon will come and kind of attack this carbon bond and forcing this the toxylate group to leave, and then through here the bond kind of just like forms.
Nice.
And then in the 6th step, this is an SN2 reaction, and it's ester hydrolysis reaction using sodium acetate. And the other, oh wait, sorry. Yeah, the ester is hydrolyzed, and then you're left with this product here. And then in step 7, you have pyridium chlorochromate, and that's used to oxidize alcohols into carbonyl groups. In this case, it's a carboxylic acid. And then in this reaction, they basically just did another Wittig reaction, and we're pretty familiar with that.
I'm a little surprised that worked with a carboxylic acid there.
Do you think it could maybe have something to do with like this, I don't know, like another, like a second step happening here?
I don't know. It's just that like Wittig reagents are, I don't know, they're sort of like anions, and then of course carboxylic acids are acids. It's a little weird to do a Wittig in the presence of an acid. Because they could have inverted the steps and made the ester first, and then it's not an acid anymore, and then done the Wittig. I mean, obviously it worked, but okay. So okay. This next thing is probably people have not seen this before. How to make that ester. Wait, the methyl ester.
Sorry, okay. I thought there was a step after this, but it's not. It's right here. Okay, so this is called diazomethane. And what that does, it reacts with carboxylic acids to produce methyl esters. And kind of what you'll see in the next step that's kind of dissimilar to Emily's reaction is that she had a ketone at before the last step. And in this case, you'll have an ester. And then in the last step, you have, you again add methyl lithium, but what happens is it kind of adds twice. So the first time it adds, it kicks out the ester, the methyl ester, and then the second time, the electrons, they move up to the oxygen on the carbonyl, and then I think it's probably quenched, and then it forms like, I don't know, like you get like these two bonds, and then it's probably quenched with some sort of like acidic water or something, or another like acid to get this, to get a carboxylic acid.
Yeah.
And that's beta Eudesmol.
Yeah. Do you know what class of compound this is? I think Beth and Lindsay's are sort of like this too. Do you know what beta-Eudesmol sort of, these are terpenes. Did you ever hear of terpenes?
Yeah.
You did it in class.
Oh, really? Yeah, terpenes are almost always made in plants, and they're multiples of 5 carbons. So if you count the carbons in this, it's, let's see, 1, 2, 3. So it's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Do you see that?
Mhm.
So all terpenes are multiples of 5 carbons, and the 5 carbon unit they come from, it's like a it looks like a 2-methyl butane core, so that a lot of terpenes have these dimethyl groups, sort of like the 2 red methyl groups on Eudesmol. That's pretty common too, that they have carbons with like 2 methyl groups in them. That's a residual from how they're made from in the plant. So chemists like to make these just because other people find different terpenes in plants, and then people try and make them just to see if they can do it.
Mhm.
Yeah.
Oh, that's pretty cool.
Yeah, but these are, you might know these as, they're called like, terpenes are oftentimes called plant essential oils. So like, I don't know what essential, like, I don't know. They like often smell nice and stuff, stuff like that. Yeah, so they're kind of pleasant actually. Anyway. All right.
Okay.
Do you have any questions for Nye or Emily?
Alrighty.
Wait, Scott, I actually have a question about our reaction. So is the ozonolysis, is that like kind of a dangerous step for the environment, or is that like a good step that they're taking ozone and using it to make this?
Well, I don't know exactly how people do ozonolysis, but you would make the ozone, you would make it in the lab, right? So
Oh, okay.
yeah, I don't know how people use ozone generators, but you might know that, like when, how like when there's a lightning storm, there's a very particular smell. That I think is ozone, because lightning makes ozone. So you can make ozone from oxygen if you irradiate it, or not irradiate it, but you like somehow electricity somehow does it. And then it also happens in the upper atmosphere just from like the high energy light that